Hello, everyone. My name is Wei Chen from Hong Kong Baptist University. I'm a year 4 PhD student under the supervision of Professor Li Chen. And today, me and Yuhan Zhao will present our recent research work fairness aware cost domain recommender system, especially for non-overlapping users. So first of all, let me introduce the motivation behind our work. Recently, cost domain recommender system getting more and more popular because it can leverage overlapping users as a knowledge bridge to improve the accuracy of the target domain. This idea sounds very promising, but we found there's some critical issues we call that cost domain recommendation overlapping bias, where the non-overlapping users may see less improvement and even performance degradations after cost domain learning compared to overlapping users. Actually, we found that in real-world scenarios, the overlapping data are typically limited. So the overlapping users may only occupy the minority of the data, while they may enjoy the majority of the benefit from cost domain learning. So we also conduct pre-experiments on this, and we found that in some scenarios, after cost domain learning, some overlapping users' performance may degrade. So this is a specific unfairness in cost domain learning. So in our paper, we also validate this kind of scenario, CDR overlapping bias, and provide analysis from theoretical perspective. Interested reader can refer to our paper. So as we see that the overlapping users, they enjoy the majority of the improvement from cost domain learning. An intuitive solution is that why don't we make all users as overlapping users? So to achieve this goal, our solution is to generate source embeddings for non-overlapping users in the target domain, so that all users can be overlapping, so all users can enjoy the benefit from cost domain learning. But though this solution sounds very promising, in practical, it faces two technical challenges. The first one is that we don't have any data of overlapping users in source domain. How can we generate their embeddings in source domain? And second, even though we can generate the embeddings for the non-overlapping users in source domain, how can we make sure they really match the source domain data distribution? So to address these challenges respectively, we propose two modules. For the challenge one, even though we don't have data, non-overlapping users data in the source domain, but we do have overlapping data in source domain. So to leverage this, for each non-overlapping users, we try to find its top n similar overlapping users in source domain, and then aggregate them to represent the overlapping users in source domain. So after that, we can generate the source embedding for non-overlapping users in source domain. And after that, we want to make sure that our generated embeddings actually really match the source domain data distribution. We employ two losses. The first one, as we do have the overlapping users in source domain, so we can use the real source embeddings and for the overlapping users to match the generated overlapping source embedding in source domain. So we employ a mean score error loss to minimize the difference of the generated embeddings for overlapping users. And after that, we also don't want the generated embedding to be identical for every users. We want that the generated embeddings can be different for different users. So here we first employ a constraint loss to make sure that the generated source embedding can be distinct from each other. So after these two components, we can make sure we can generate a source embedding for non-overlapping users and make sure the generated embeddings can match the real source data distribution. So so that we can make all users in the target domain overlapping, so all users can enjoy the benefit from the cross-domain learning. So to validate the effectiveness of our proposed VUG, we conduct experiments on 3 real-world data sets with different data statistics. In terms of the accuracy metric, NDCG and Hit Ratio, and fairness metric, unfairness UGF, where the UGF actually measures the absolute accuracy difference between the overlapping and non-overlapping users. Furthermore, as our decided VUG is model agnostic, we can integrate it into any existing CDR baseline to validate its performance. So here is our major results. The major focus is on the UGF, where the lower UGF indicates better fairness performance. So from the right side of the figure, we can see that our proposed VUG largely improved the fairness performance. On the other side, we also examine the overall accuracy. We can see our proposed VUG also slightly improved the overall accuracy performance. That's good. So after that, we also examine the contribution of each component we propose in terms of both accuracy and fairness. And in conclusion, all components positively contribute to the VUG's accuracy and fairness performance. Here, though we already shown the effectiveness of our proposed VUG, some may also concern that integrating our VUG will make the model too complex and inefficient, so it may be impractical in real-world deployment. So to address this kind of concern, we conduct a small experiment on a small data set. And in conclusion, is that integrating our VUG only slightly increased the total training time of the cross-domain learning, so which make it may be more practical in real-world deployment. So in conclusion, in this paper, we address a critical unfairness issue called CDR overlapping bias in cross-domain recommendation by proposing a VUG, virtual user generation framework, to make all users as overlapping users so they can enjoy the benefits from cross-domain learning. And in our future, we would like to explore maybe some other unfairness phenomena in other cross-domain methods, such as review-based cross-domain recommendation, which may be maybe based on overlapping items. And we also would like to explore the application and deployment of our VUG in real-world industrial scenarios. Okay, that's today my presentation. Thank you. Okay.
What happens when the source domain itself is biased or noisy? Doesn't that risk transferring the bias to all target users?
Maybe your question is like when the source domain data is biased, how's the performance? Or indeed, we found like in our experiment setting, we found that for different data set, it have different data statistics. Like some data set may have more overlapping, and some data set may have less. And in the source domain, even only for the single domain in the source, they may have different data distribution, but the one key point is that the introducer of the source domain can increase the informations for the target domain training. So even though sometimes it's biased, but it can also provide some useful information. So finally, we can leverage such kind of information to improve the final performance.